The Internet Protocol plays a vital role in the Internet Protocol Suite by facilitating communication across network boundaries through the transmission of datagrams. These datagrams contain information necessary for routing and are used to deliver data from a source host to a destination host based on unique IP addresses. IP operates independently of a connection, establishing the groundwork for the Internet by defining packet structures that encapsulate data to be transmitted and implementing addressing methods for effective labeling of the datagrams. Initially introduced as part of the Transmission Control Program in 1974, IP was designed to provide a connectionless datagram service. It works in conjunction with the Transmission Control Protocol, forming the widely recognized Internet Protocol Suite known as TCP/IP. The predominant version, Internet Protocol version 4, has been the cornerstone of the Internet, with its successor, Internet Protocol version 6, gaining traction since around 2006. The primary functions of the Internet Protocol include addressing host interfaces, encapsulating data into datagrams, handling fragmentation and reassembly, as well as routing datagrams across IP networks. Each datagram consists of a header containing the source and destination IP addresses, along with essential metadata for routing, as well as a payload that carries the actual data. Through the process of encapsulation, the data payload is nested within the packet header. The IP addressing system involves assigning IP addresses and associated parameters to host interfaces, dividing the address space into subnets by specifying network prefixes. IP routing is executed by all hosts and routers, with routers communicating using specialized routing protocols, either interior or exterior gateway protocols, based on network topology. Addressing methods in the Internet Protocol encompass 4 key approaches. Unicast, which targets a single node with a one-to-one association between sender and receiver. Broadcast, which dispatches messages to all nodes in the network with a one-to-all association. Multicast, delivering messages to a group of nodes interested in receiving it using a one-to-many or many-to-many association. And Anycast, sending a message to a single node from a group of potential recipients based on proximity to the source. The evolution of Internet Protocol versions has been marked by significant milestones, beginning with the foundational work of Vint Cerf and Bob Kahn in the 1970s, leading to the development of IPv4. The subsequent iteration, IPv6, introduced 128-bit addressing, a significant upgrade from the 32-bit addresses of IPv4. While the transition to IPv6 has been gradual, its adoption has steadily increased globally, with many countries embracing the protocol to accommodate the growing demands of the Internet. The version history of IP demonstrates the ongoing efforts to enhance communication protocols and address the evolving needs of network connectivity in the digital age. The Internet Protocol Suite's design adheres to the end-to-end principle, which was originally derived from the Cyclades project. This principle views the network infrastructure as inherently unreliable at any single point and in a constant state of flux regarding the availability of links and nodes. Unlike traditional approaches, there is no central monitoring or performance tracking system in place to maintain the network state. In this decentralized model, the intelligence resides in the end nodes to reduce network complexity. As a result, the Internet Protocol offers best effort delivery, leading to an unreliable service. It operates as a connectionless protocol, in contrast to connection-oriented systems, with no stored routing information from previous packets, causing packets to potentially arrive out of order. Various fault conditions can arise, including data corruption, packet loss, and duplication, which must be detected and managed by the end nodes. The upper layer protocols within the Internet Protocol Suite handle reliability matters. For instance, hosts can buffer network data to ensure proper sequencing before delivery to an application. IPv4 includes mechanisms to ensure error-free IP packet headers, discarding packets with failed header checksums at routing nodes. The Internet Control Message Protocol, ICMP, can notify errors, although routing nodes are not obligated to inform either end node of errors. In contrast, IPv6 does not utilize header checksums, assuming the link layer technology offers adequate error detection capabilities. The Internet's dynamic nature and diverse components mean that there is no assurance that a specific route can effectively transmit the requested data. Technical limitations, such as the maximum packet size on a given link, come into play. Path Maximum Transmission Unit, MTU. Discovery can assess the entire path's MTU for effective communication. In IPv4, when the link MTU is exceeded, datagrams are automatically fragmented for transmission, with IP handling reordering of received fragments. Unlike in IPv4, an IPv6 network does not fragment at network elements, necessitating end hosts and higher layer protocols to stay within the path MTU limits. Protocols like TCP adjust segment sizes to fit within the MTU, while UDP and ICMP can lead to IP fragmenting oversized datagrams.